Welcome back, Calc. I hope you all are doing well. Our objective today is going to be to analyze equations of tangent lines, but in regards to concavity. So a lot of this should look really familiar. We're just going to add on what concavity has to do with this, and this is actually going to give us a way to say whether our estimations are a little bit too much or a little bit too small compared to our actual value. So I've got the checklist on the screen. You know what to do from here. All right, I'm actually going to force a pause on your screen. Can you do me a favor and write the equation of the tangent line of y equals x squared at the point 1, 1, and then go ahead and hit continue when you are ready to see the answer. Okay, we should have gotten y minus 1 equals 2, which was our derivative at x equals 1, times the quantity x minus 1. All right, so let's take a look at the graph here, both of the original y equals x squared as well as the tangent line. And I want you to notice, how does concavity play into this? So let's take a look at the graph. All right, so I've graphed the original, my good old standard parent function y equals x squared in red, as well as the tangent line you got. So that looks nice. I can tell if I zoom in on that point of tangency at 1, 1, the red and the blue start to look the same, right? Which is why we like tangent lines, because they can make predictions for us. And lines are, the easiest function to work with. So even if I don't know what the original function is, if I have the ability to draw the tangent line or write the equation of that line, I can make some predictions. Now, we've done that part. We've done all of this already. Like if I were to say, use the equation of the tangent line to predict now f of 1.3, then I could just plug in 1.3 into my tangent line equation and solve for x, right, or for y. Now, what I want you to notice, though, is let me go ahead and highlight points on both the red parabola and the blue line, and let's go ahead and play the slider here. So you can see that the farther I get from that green dot, that point of tangency, the more they start to diverge, right? The more they become different. Furthermore, what do you notice about the red y value versus the blue y value? The red is always going to be larger than the blue. The red dot always sits above the blue. Let's come to the other side of that point of tangency. You see they're starting to diverge. And once again, the red is always larger than the blue. So we're going to come to this conclusion that if I were to use my tangent line, in this case the blue dot, to approximate my actual value, in this case the red dot, I'm a little bit too small, right? This is called an under approximation. It's a little bit lower than what it actually should be, right? And again, the closer I am to that point of tangency, the closer the values are, and the farther I get, the more that they diverge. They become their difference becomes larger, right? So our conclusion is, okay, we can use these tangent lines, again, as long as we stay close to that point of tangency. And what do we think about the concavity? So if my original function is concave up, like in this case, my tangent lines are always going to sit underneath, okay? Meaning our tangent line approximation, also known as your local linearization, is going to be an underestimate. Now the opposite will be true if you're concave down, right? My tangent lines will sit above, and so you'll get overestimates. So let's please put that in words. All right, so let's write this. If f of x is concave up, then our local linear approximation is an under approximation. Okay, it's slightly lower. That's what we had in our scenario here, right? So concave up, remember one of the definitions of concave up is that your tangent lines sit underneath it, okay? And then the converse, if f of x is concave down, then our tangent lines sit above our curve, and our approximation using that tangent line is slightly higher than the actual curve. So approximation is over. All right. Okay, so let's try a couple examples and see how this might show up on the AP exam. All right, I'm going to force a pause on your screen. You don't need to write all of this, but can you just, in your notes, write example 1 and then what I have in blue? Okay, we're back. So part A says write the equation of the line tangent to G at 3. We've done this before, right? And you'll see this pop up on the AP exam. It's like your classic calculus problem. You'll see it pop up quite a bit, okay? So whenever I see write the equation of the tangent line, I think point slope form. So y minus y1 equals m times the quantity x minus x1. Now, x1 needs to be given. And they're saying write it at 3, okay? So when x is 3, what is y? y is 1, right? So I've got y minus 1 equals, now the derivative gives me my slope of the tangent line. So when x is 3, what's the derivative? It's 2, right? So I've got 2 times the quantity x minus 3, okay? And that's part A. Very, very common part A, especially on an FRQ. You'll see it's kind of scattered throughout multiple choice as well. Okay, so now part B. Use this line to approximate g of 3.1. We've done that before as well, right? So let's do that first. I'm going to plug in 3.1 for x into what I got in part A, okay? So I'm going to have y minus 1 equals 2 times the quantity, 3.1 minus 3. All right, so now I do need to go ahead and solve for y here because we want to approximate g of 3.1. So I'm going to have y minus 1 equals 2. 3.1 minus 3 is 0.1. So y minus 1 equals 0.2. So this gets me that y is 1.2. Let's do this. Okay, so y is 1.2. So that's going to be an approximation for g of 3.1. Okay, so now it says, is this an over approximation or an under approximation? Justify. Well, according to the notes we just took, we need to know the concavity of g. But notice, they don't talk about the concavity of g. However, we are given the sign of the second derivative. Well, if the second derivative is positive, g must be concave up, right? And if the graph is concave up, the tangent line we just drew has to sit underneath. So this is under approximation, and you can just do approx there, since g double prime of x is positive, or you can say since g is concave up. Either way, those are synonyms, right? Good deal. All right, I'm going to force another pause on your screen. Again, you don't need to copy it all, just the blue letters, terms. Okay, we're back. So we want to use a linear approximation, so that's just a fancy word for tangent line, right? To estimate the function value given the following information, then determine whether your approximation is over or under, and for that I need to know the concavity of the original. Once again, I don't see them talking about the concavity of f. I also don't see them talking about the sign of f double prime. But notice they do talk about the increasing behavior of f single prime. So thinking about your Peterson diagram, if f single prime is increasing, what can you tell me about f? F is concave up, okay? So we actually do know the concavity of f, right? All right, so let's try this one. So we've got y minus 7 equals m, which is 1, times the quantity x minus 3 as our tangent line, right? Now we are going to plug in 3.01 for x. So I've got y minus 7. That 1 I don't need, right? 3.01 minus 3. So I get y equals, let's see, this is going to be 0.01, and if I add 7 to that, I'm going to get 7.01 for my approximation. Now again, since f is concave up, that tangent line I just drew is going to sit underneath. So this is going to be an under approximation, since f prime is increasing, or if you prefer, since f is concave up. Either way. All right, that is all I have for you. I will see you all next time.